So this is the first video in CC2, which is a topic about pure and impure substances and separating mixtures, and it is a paper 1 only topic. We're first going to look at the difference between a pure substance and a mixture. Below, I have drawn out a couple of examples of pure substances. So here on the left, I have got pure gold. Because gold is a solid, I've arranged the particles as a solid, and you can see, well, it's a bit small, but each particle is the same. Each particle is an atom of gold, so I've written the symbol AU. Because all of the particles are the same, this is a pure substance. In the case of gold, each individual particle is an atom. Next up, I've got oxygen gas. Because it's a gas, I've got the particles drawn as a gas. Oxygen gas, oxygen is always present as O2, not just O. So in this case, each particle is not an atom, each particle is a molecule. The molecule contains just 2 oxygen atoms, so I've only got oxygen. And again, because I've only got O2 molecules, it is a pure substance. Next up, I've got H2O, which is a liquid, so I've drawn the particles kind of touching each other. In H2O, you've got 2 different elements. You've got hydrogen and you've got oxygen, but they've combined to make 1 molecule of water. Because all of my molecules are exactly the same, this is still a pure substance. So just because I've got more than 1 element doesn't make it impure. Hydrogen and oxygen combine to form water. I've only got water molecules present. This is pure water. If we look at an example of something impure, so this is a mixture, all right? I've drawn oxygen gas again, but this time instead of only having oxygen gas, I've now also got carbon dioxide gas there too. So it's not just oxygen, I've also got CO2. Because I've got 2 different gases mixed together, I can say that it's impure or it's a mixture. If I wanted to make my water impure, I would have to add something else in there. So I could add salt, I could add sodium chloride. And if I had little sodium and chlorine ions drawn in there as well as my H2O, well then I've got 2 different substances and that would make it impure. So pure, made of just 1 type of substance. Impure is made of more than 1 type. You can tell the difference between a pure substance and an impure substance by looking at their melting point. So in the last video of CC1, we looked at heating curves, and I'm going to draw something similar here. So I'm going to start off by drawing the heating curve of a pure substance. So let's just say I'm drawing the heating curve for pure water. So I'm starting off below 0 degrees Celsius. So water is going to be a solid, it's going to be ice. And I heat up my water, and when I hit 0 degrees Celsius, my water is going to melt because a state change is occurring. I have a constant temperature, so it's a flat part of the graph, and then I continue to heat my liquid water. So I have a flat part of the curve when my water is melting. And you can see that the melting is taking place at 0 degrees Celsius, okay? If you're unsure of why I'm drawing a flat part of the graph there, go back and watch the video for CC1 part 2. That is my pure substance. This is pure water. If I had an impure substance and I started to heat it, so I'm just going to say I'm heating my impure substance now. I'm just going to heat it a little bit stronger so I can draw the line differently. Just say I'm heating my impure substance now. You're also going to get a state change at one point. So imagine I'm starting off as a solid. It's going to become a liquid. I am going to get a state change. But instead of having a really flat part of my graph, I end up with something that looks slightly different. The reason I don't get a totally flat line is because the substance is impure. The substance doesn't all melt at exactly the same time. So this line here does represent melting. In the pure substance, that line was totally flat because the entire substance melted at 0 degrees Celsius. Here, because I've got different substances in my mixture, they don't all melt at exactly the same point. So I could say it starts melting at like -2 degrees Celsius and it doesn't finish melting until 5 degrees Celsius. And the reason you get that range in temperatures is because the substance is impure, they don't all melt at exactly the same time. So you can use melting points to tell the difference between a pure and an impure substance. So if we just look at some sample questions here. The first example is identify which of the substances below are pure and which are mixtures. So they've drawn out a light grey circle, a white circle and a black circle. In the first one you can see that you've only got these light grey circles, all particles are the same, this is pure. C, you've only got the white circles, so C is going to be pure, and E, you've only got the black circle. So A, E and C are all clearly pure. I've got a solid, I've got a gas and I've got a liquid. If we look at D and B, you'll see a mixture of the circles in both. In D, you've always got a black circle surrounded by 3 white circles. So that structure is exactly the same. So I would say D is pure, but it's a pure compound. Okay, you've got, this could be something like NH3, for example. You've got the same arrangement of atoms in each molecule, it is pure. B, on the other hand, you've got a mixture. You've got some cases where you've got a black and a grey circle together, and then you've got others where it's just a white circle floating around. So you've got 2 different substances mixed together. B is going to be your mixture. The other question is about the melting points. It says substance A melts at 50, substance B melts from 70 to 75, which is pure and which is impure. A has got a definite melting point, that means it's pure. All of A is the same substance, it all melts at exactly the same point. With B, you've got a melting point range. It starts to melt at 70, it doesn't finish melting till 75 because you've got different substances in B. So A is pure, definite melting point, B impure because it melts over a range. So I've got an example exam question here. I want you to do question 1 and, well, question 5. So just press pause and have a go and then press play for the answer. Okay, so I've done out the answers. The first one, how can I tell that this is a gas? I know it's a gas because the particles are all far apart and they are randomly arranged. So you can use the word particle, or you could have said molecules there because they are molecules, but using the general word particle is fine. They're far apart, randomly arranged. How do I know it's pure? You've only got one type of substance. You could go further and you could explain that each molecule has a nitrogen and an oxygen atom and that all of your molecules are exactly the same, but just saying that you've only got one type of substance is enough for why it is pure. The next one, which of these is a mixture? So in the first one, you've just got chlorine, that's pure. Just got sodium, that's pure. I know you've got sodium chloride, so you might be thinking, oh, I've got 2 different elements, that makes it a mixture, or that makes it impure, but it doesn't. So sodium chloride is salt. You can have pure salt, pure sodium chloride, that's absolutely fine. Just like you can have pure water, which would be H2O, just because you've got 2 different elements present does not make it a mixture. But the last one, sodium chloride solution, that word solution means that you've taken sodium chloride and you've dissolved it in water. So you've got a mixture of sodium chloride and water. That makes it impure. So moving on from that exam question, we're now going to look at how to separate mixtures. So if you do have a mixture, if you've got 2 different things in there, how are you going to separate those 2 different substances? And there's one thing you have to be super clear on, and that is the meaning of the following words. If you've got a soluble solid, it is a solid that will dissolve in a liquid. If you've got an insoluble solid, it is a solid that does not dissolve in a liquid. And if it is soluble, you will use crystallization to separate. And if it's insoluble, you're going to use filtration. So it's really important that you're familiar with these 2 words so that you know which technique to pick. So we're going to look at filtration first, which is how you separate insoluble solids from liquids. So if you just think of an everyday example, right? So if you are making pasta and you boil pasta in some water, and at the end, when you're finished boiling it, you want to separate the pasta from the water. Okay, pasta is an insoluble solid. The pasta doesn't dissolve in the water, and at the end, when you want to separate them both, you use a strainer. It's like a filter. And that's exactly what you're going to use in chemistry. If you've got an insoluble solid, you're going to use a filter to separate it. you do need to be able to draw this, okay? They could ask you to draw this, to draw a diagram to show filtration. And generally, diagrams get a little bit patchy. So the first thing you need to do is draw your glassware. You don't use a beaker in filtration, you use a conical flask. It doesn't have to be a work of art, okay? But that is your conical flask. So you don't use a beaker, you use a conical flask. And the reason is the conical flask has a narrow neck, and you're going to be placing a funnel into your conical flask. And because you've got the narrow neck, the conical flask supports the funnel, whereas a beaker does not. So your funnel will be allowed to just sit in there. So that's your funnel. And you can see in my funnel that I've got a pretty big gap here. So if I had quite a small solid and I just tipped it in, it would just pass straight through that funnel and I would collect it at the bottom, which is not what I want. So what I'm going to be using, what I'm going to be putting into my funnel is I'm going to be putting in filter paper. So I'm just drawing another double line there. And that is going to be my filter paper. And the filter paper has tiny, tiny holes in it. So it will allow the water to pass through, but it will hold the solid in the funnel. So then you'll take your mixture, whatever it is. So just say you had a mixture, so you don't really need to be able to draw this part of it, but just say you've got your beaker and you have got, I don't know, some form of insoluble solid. So because it's insoluble, I can see my solid in the beaker, and then I've got my liquid. I'm going to take this, I'm going to pour it through, and what will happen is that the liquid will all pass through those tiny holes in the filter paper, but the solid will be held in the filter paper and you will have separated them. Okay, there is specific words for the solid that's left behind. So the solid that's left behind is called the residue, and then the liquid that passes through is called the filtrate. Okay, so I'm gonna give you a look at some kind of typical questions that they might ask. So how would you separate a mixture of sand and water? So sand does not dissolve in water, so you would use filtration. Because they want, it's not a state question for 1 mark, they want you to actually talk about how you would do it. So you put the filter paper in the funnel, you put the funnel in the conical flask, and you slowly pour your mixture through the filter funnel. How does it work? Okay, so the liquid is going to pass through the filter because you've got tiny little holes that allow the liquid to pass through, but your insoluble solid is going to be collected because the solid particles are too big to fit through those tiny holes. The piece of glassware, as I mentioned, is the conical flask. You need the neck to hold the funnel. Why is it not suitable? So if you had salt and water, salt actually dissolves in water. So if we go back to my pasta analogy again, just say you had salted the water before you added the pasta in, that salt immediately dissolves in the water. And when you pass your pasta water through the filter, all of the water, including the salt, just passes straight through that strainer. And the reason is because the salt is dissolved in the water. Because it dissolves, it does pass through the filter paper. Dissolving splits the solid up into tiny, tiny, tiny ions that are then capable of passing through the tiny holes in the filter paper. So it's not going to work. And that brings me on to the method that you are going to use. So if you have a soluble solid, so if you have a solid that is dissolving in your liquid, then you're going to need to use crystallization. And again, you could be asked to draw this, but it's super straightforward. You're going to draw what we call an evaporating dish. You are going to place that evaporating dish on a tripod, and underneath your tripod you are going to have a Bunsen burner. Okay, so in here you'll put your, I'm just going to say our salt and water, so that would be an example. This is called an evaporating dish. And then you heat it. And what will happen is that when you heat this mixture, the water has a boiling point of 100 degrees Celsius. So at 100 degrees Celsius, it will become a gas, okay? It will evaporate and become a gas and it will escape. Your salt has a much higher boiling point, actually, it's much higher even melting point. So your salt is going to remain a solid even when you heat it, and it will be left behind in your dish. So it's not even going to become a liquid when you're heating it. It's got a much higher melting point. Salts are ionic compounds, and they've got really high melting points. So yeah, you'll evaporate all of your water, you'll be left with your salt. When you're doing this, you shouldn't heat it really quickly, okay? If you heat it really quickly, you'll evaporate the water really quickly and you'll be left with a kind of mush. So what you want to do is you want to heat it to evaporate half of the water, and then the rest of it you want to let evaporate slowly overnight. By doing that, you'll form nice big salt crystals. If you heat it really quickly, you're just going to end up forming mush. So again, your worked examples. Sodium chloride is soluble. How are you going to obtain pure sodium chloride? So it's soluble, it's dissolved in water. You need to get rid of the water so that you've got the pure salt. So you heat the mixture to evaporate. You have to mention heat. You actually get a lot of marks for being able to describe this process, but you need to describe it in detail. So you need to mention heat in your answer. It's not enough to just say evaporate. You have to say how you evaporate. So you heat to evaporate some of the water. Some of the water, okay, you don't evaporate all of it at once. You let the remaining water evaporate slowly, and then you're going to leave your salt crystals to dry. And again, you're evaporating slowly, so you form larger salt crystals. And yeah, that's explained here. Why did he let it evaporate slowly? Why did he turn it off? Because you want to evaporate slowly so you get large salt crystals. Okay, so there's two different methods of separation. Filtration for insoluble solids, crystallization for soluble solids. Both of these methods of separation come up in the acids topic because we talk about making salts, and you're often asked to describe how to make a salt, and you have to describe these processes. So you can be asked, an individual question on separating mixtures from CC2, or they can incorporate it into CC8 when you're talking about acids. So it is content that comes up all of the time.